My name is Deeban Chakravarthy. Along with my teammates Sai Sathish and Vasanthan, together we are here to present our work on secure low-power FPGA design for detection of camouflage attacks in SOC devices. Under the guidance of our respected faculty advisor, Mr. S. Palanivel, we embarked on this journey with the aim of addressing a critical challenge in the field of embedded systems and hardware security. In our presentation, we will delve into the intricacies of FPGA design, focusing on its low-power consumption while ensuring robust security measures against camouflage attacks in system-on-chip devices. Together, we have poured our efforts into this project and we are eager to share our findings and insights with you today. Let's see about the contents in this presentation: objectives, aim and scope, literature review, research gaps, existing system, problem statement, proposed work, results, and references. Let's see about the objectives of this project. To create a versatile test circuit generator incorporating sweep generators, clock synthesizers, and digital PLLs with configurable architecture and low power techniques to evaluate FPGA functionality, and to develop a stable reference clock generator derived from global signals for precise timing in SOC devices, and to design a digital circuit-based attack pattern generator capable of simulating diverse attack scenarios such as side channel attacks, FPGA replay attacks, and corruption attacks, to implement a dynamic pattern matching algorithm to detect and validate different types of attacks, enhancing SOC device security, and to integrate all modules into a cohesive framework using fine-state machine processors to ensure seamless operation and interoperability while maintaining system performance. Now let's dive into aim and scope. The primary objective of this project is to develop and validate physical attack detection modules for enhancing the security of system-on-chip devices, to explore and evaluate the effectiveness of various clock tree synthesizers in detecting and mitigating physical attacks targeting SOC devices. The project encompasses investigating and addressing clock-related issues in SOC devices through the testing and validation of FPGA chips with multitasking clock synthesizers. The project also involves integrating dynamic pattern matching algorithms and attack pattern generators into SOC devices. These are the literature review survey we have referenced in this for this project. The first paper from Journal of Hardware and System Security. The study showcases physically unclonable functions as effective tools for bolstering device authentication and secret key generation in hardware systems, enhancing security measures. And the next paper, titled Increased Output Corruption and Structural Attack Resilience for SAT Attack Secure Logic Locking from IEEE Transactions on Computer-Aided Design of Integrated Circuits and Systems, demonstrates enhanced output corruption and structural attack resilience in SAT attack secure logic locking, presenting promising advancements for securing integrated circuits against malicious attacks. And the next paper, titled On the Foundations of Physical Unclonable Functions from IACR Cryptology ePrint Archive, highlights the fundamental principles underlying physical unclonable functions, elucidating their pivotal role in bolstering hardware security against unauthorized access and tampering attempts. And the fourth paper, titled PUF-Based Cryptology, a New Paradigm for Security of Integrated Circuits from IEEE International Conference on RFID. It is a comprehensive review of the transformative potential of PUF-based cryptology in bolstering the security of integrated circuits, introducing a novel paradigm to thwart unauthorized access and ensure data integrity. And the last paper, titled A New Logic Locking Scheme Resilient to Gate Removal Attack from 2020 IEEE International Symposium on Circuits and Systems. The research introduces a novel logic locking scheme designed to withstand gate removal attacks, offering enhanced security measures for protecting integrated circuits against malicious tampering. Let's see about the inferences from the literature review. All the papers deal with hardware security concepts like device authentication, secret key generation, and logic locking within integrated circuits. This suggests a growing focus on securing hardware components against various attacks. The references discuss attacks like SAT attacks and gate removal attacks. This implies that researchers are actively identifying and addressing new security threats that emerge alongside advancements in hardware technology. PUFs can generate secret keys, providing a secure way to encrypt and decrypt data on a device. PUFs are resistant to physical attacks such as copying or cloning due to their unique and unclonable nature. Let's see about the research gaps. limited exploration of integrating voltage-based sensors with logic clocking techniques for attack detection, and insufficient evaluation of simulation models that consider both physical and logical security threats in SOC devices. Lack of studies on the effectiveness of hardware security mechanisms under varied and simultaneous physical and logic attack scenarios. These are the research gaps from the literature survey. Let's see about the existing system. In the existing system, the scenario pertains to a physical attack targeting system-on-chip devices. The attack's impact on these devices is assessed using two-fold clock and voltage-based sensors within a VLSI simulation. This simulation aims to demonstrate the effectiveness of an attack detection mechanism in a hardware security context. Now let's see about the problem statements in the existing system. The current system only analyzes physical attacks on SOC devices, neglecting other potential threats like software or side channel attacks. SOC devices faces security risks from multiple attack vectors like side channel, FPGA replay, and corruption attacks. Current defenses are often limited and may not fully protect against diverse threats, leaving devices vulnerable. Improved adaptable defense mechanisms are needed to enhance SOC device security comprehensively. The validation of the voltage modulation sensor is only twofold, potentially missing crucial aspects of sensor performance under various attack scenarios. Now let's see about the proposed work. To overcome various clock issues in system-on-chip devices, multitasking FPGA chips need to be tested and validated with various attack detection modules. Here, an in-depth analysis module is created to test the FPGA devices with multiple clock tree synthesizers such as sweep generators, configurable clock synthesizers, digital phase clock loop, etc. This type of simulation is essential for evaluating the robustness and security of SOC devices and can help in designing more secure hardware systems. Now let's see the key features of proposed system. Multi-attack detection. The system tackles various attacks like side channel attacks, replay attacks, and corruption attacks, offering a broader security assessment for hardware. And configurable testing. The system allows adjusting test parameters, enabling simulations of diverse hardware behaviors and potential vulnerabilities. And dynamic pattern matching. The dynamic pattern matching algorithm adapts to identify even new attack patterns, improving resilience against evolving threats. And last, efficient design. The system focuses on efficient operation, potentially making it suitable for resource-constrained hardware platforms. And now the proposed work block diagram. Global FPGA clock and global FPGA reset, reference clock generators, and low power techniques like sweep generators, configurable clock synthesizers, and digital PLL are used. And the attacks, side channel attack generator, corruption attack generator, and FPGA replay attack generator are used to generate various attacks. And the attack weight analysis analyzes the counters. And then the dynamic pattern matching algorithm compares the reference signal and the input signal, and the area, power, latency are measured, and the attack types are classified by using the dynamic pattern matching algorithm. Now let's see about the advantages. Attack detection tests for various physical attacks, not just laser injection, for more robust security evaluation. Stronger clock security analyzers, clocking systems with diverse synthesizers to identify and address clock manipulation vulnerabilities. Multi-resource stress tests stresses resource allocation by testing with multiple clock distributors, revealing potential weaknesses during complex clocking scenarios and potential attacks. Realistic attack simulation simulates a wider range of clock manipulation attacks using diverse clock synthesizers for a more realistic security assessment. Enhanced SOC security ultimately contributes to designing more secure system-on-chip devices by thoroughly testing and validating multitasking FPGAs with physical attack detection. These are the results we got from models and software by compiling and simulating all the VHDL codes. Each attack has its own configurable value. By seeing the abnormalities in the waveform and the bit values, the generated attacks are detected. This is the waveform that we got from the entire design of the project. This code is from the testbench lab, which integrates all the components of the project. Let's see about the pattern learning algorithm which is used in this project. The input is the test data and the output is the difference trigger pulse and the count of anomaly. For every rising edge, the frame size is initiated for first 100 pulses, and if the global clock is equal to 1, the level is checked and a rising edge counter is incremented, and if the rising edge is low, the counter stays the same and the glitch status will be 1, which indicates the side channel problems. This is the schematic view of logic attack detector and RTL schematic report. RTL schematic is the visualization of the hardware descriptive language. Now let's see about the power supply summary. The total power supply taken for this project is 22.66 milliwatts and the dynamic supply power is 8.86 milliwatts and the quiescent supply power is 13.79 milliwatts. Now let's see about the latency summary. The total real time to XST completion, the XST is a Xilinx simulation tool, taken is 3 seconds and the total CPU time to XST completion is 2.96 seconds. Total memory usage is 249084 kilobytes, which will be around 243 megabytes. The number of errors are 0 and the filtered is 0. The number of warnings are 45 and the filtered warnings are 0. The number of infos are 3 and the filtered infos are 0. Now let's discuss about the future works. Advanced clock management. Investigate more sophisticated clock management schemes that could adaptively change clock's characteristics in response to detected attack patterns. This could involve developing smarter AI-driven clock synthesizers that adjust dynamically to the security context. And hardware obfuscation techniques. Develop and test various hardware obfuscation techniques that can make it more difficult for attackers to decipher the logic and state of a chip using techniques like LLSI. This could involve dynamically reconfigurable logic and randomization of critical paths. Real-world testing and validation. Extend the simulation-based testing to real-world scenarios where FPGA devices are tested under actual operating conditions and against sophisticated physical attack methods to validate the effectiveness of the proposed security measures. These are the references that were considered for our project. Thank you.